Yeah, all right. Since this is the second last lecture now, and we're doing something a little bit different today when we start with ray tracing, a little bit different than what we did before, I thought we could start with looking at some nice state-of-the-art computer graphics. And of course, what better place is there to look for state-of-the-art computer graphics than Pixar? So let's just look at the quick movie.
Russell, what are you doing?
I'm making an official Wilderness Explorer snipe trap. And as soon as a snipe steps right... Ah! Help! Thanks again for saving my life, Mr. Fredrickson. And now for the perfect snipe bait. No animal in the entire universe can resist chocolate. Whoa! Help! It looks so chocolatey.
Russell, if you...
Maybe if I'm really quick.
Wait!
Oh. Want some?
All right, yeah. So I hope you also looked at the graphics and not just at the movie, at the rendering, at the shadows and the lighting, the shading. So I also searched for a clip from the new Cars movie from Pixar, who's supposed to come out soon, but I found this clip a little nicer, so I thought I'd bring that one. I have another one, which is actually from the related video game.
Rated E10 for ages 10 and up.
This summer, discover a lost world. Disney Pixar Up, the video game. Hold on for an amazing journey. Travel through undiscovered jungles of South America.
That bird's in trouble.
Battle dangerous creatures.
Careful, Russell!
Avoid getting captured. And experience the jungle adventure of a lifetime.
He doesn't like the eel! Scramble all fighters and take down that house!
Disney Pixar Up, the video game. Adventure is out there.
All right, so yeah, of course the reason why I was showing this was not only to entertain you, but also I had an intention behind this. If you looked at the graphics, at the rendering, you saw that the video game looks much, worse or less realistic as the movie does. And of course, you can argue now maybe this is just a specific video game, and also the movie, of course, these are cartoon characters, so they didn't really try to animate them really like actual humans, but they made them this cartoon characters. So if you would try to really render a real human and animate it, it would of course look different. But in any case, I said I looked also in the Cars movie, and then also you see if you compare the movie, which is really the latest state-of-the-art in rendering, with the video game, you see that there is of course a huge difference in terms of the graphics. If you look at it, of course at the projector you don't see it that nicely, but if you look at the videos later and the recordings or the slides when you download them, or I mean, you know it also from yourself when you play video games. I think there are of course video games that have a much better graphic than this one, but usually there is a difference between when we watch a movie and we play a video game. And the reason for this is of course the rendering, because you have in a computer game you always have interactivity, so you have things that have to change in real time based on your actions, whereas for a movie you render that once and then you can play it over and over again, and you know exactly what the next frame will look like. So you do that once and you can spend a larger amount of time on rendering it. You don't have to react in real time, which is why in practice, like computer games are usually implemented with a hardware pipeline, whereas this here is often done with a software pipeline. And the advantages and disadvantages of these are should be clear. With a hardware pipeline, you are usually much faster. So you have this, you can achieve real-time graphics that look pretty good. But of course, you're suffering from, of course, when you make it real time, you cannot use all kinds of fancy rendering techniques that take too long to process. But also, you're kind of a little restricted to what the hardware allows you to do. Whereas if you have a software pipeline, you have much more freedom. And of course, if you make a movie, you also have much more time to do the rendering. And yeah, so in this course, of course, we're only scratching the surface and only covering the basics, but I thought it's also quite nice to look at the, yeah, not real stuff, but at the final high-end stuff that maybe in a couple of years when you finish with your studies, you can create more fancier graphics than you can after this course. And also Bas and Maurice will today tell you something in this other talk about current state-of-the-art graphics and rendering. And also this is kind of interesting, especially when I talk about the performance and the performance in terms of rendering time. It is kind of interesting to what we want to talk about today, which is in contrast to this pipeline projection-based approaches, the ray tracing approach, which is much slower, usually much slower. Of course, it always depends on how you implement it. There's also fast ray tracing, but it's usually much slower than the projective methods, which is why it's usually not used in games and less frequently used in movies. But on the other hand, we have the advantage that the approach produces very realistic results. So yeah, so some of you might wonder, okay, why should I care about ray tracing at all? I'm interested in game programming, so who cares about something that I cannot use there? But first of all, I mean, these techniques approach each other. So you see, meanwhile, also a lot of real-time rendering graphics in real time, and you see now we're doing now. Maurice told you that not that long ago we had a fixed pipeline in hardware. Now we have a programmable pipeline, so you are already able to do more, which means you can do better, more realistic rendering, and that will of course improve in the future. The hardware gets faster, you have new methods and new hardware, and you can do better rendering in real time. At the same time, the software also improves, so we have faster and more realistic software pipelines. And of course, for ray tracing, they're also working on making it faster, improving it, having hardware support. And there is a trend towards real-time ray tracing. So there is a chance that in the not so far future, you will run over ray tracing even when you're programming a game, which right now you usually don't do with ray tracing. The other reason is, of course, why you should be interested in ray tracing. If you study computer graphics, then you should have like a larger overview of the whole field, even of the parts that are not directly relevant for you, because many of the techniques that you will see today when we use for ray tracing are actually pretty much related for projective methods. Some approaches are even direct application of stuff that we already discussed. Actually, most of it, what we will discuss today, is related to things or based on things that we already discussed. A few new things will come, maybe not today, but next time, that are purely originally ray tracing techniques, but they are also important for programming real-time graphics with projective methods, especially in relation to game programming. So this is another reason why it should be interesting for you. And finally, as I said, there are a lot of similarities, and we're approaching the end of the course, so it's also a good opportunity for you to repeat that and look again at the old stuff that you hopefully learned, or if you realize you haven't learned it, then you know what you can do in this next week, where you have a little more free time because there's only one lecture. All right, yeah, so there will be a lot of repetition today, as I said, and yeah, you see, you already see that this is pretty much the same as one of the slides that I put on in the very first lecture, where I introduced computer graphics and said that there are three major areas usually covered. One is the modeling, the creation of the 3D worlds. Then it's the rendering, which is the bringing the 3D worlds on a 2D screen. And then the last step that is often considered part of computer graphics is animation. And I also told you at that time that we will not talk about the animation and not about the modeling. There are separate courses for this. For modeling, there's the 3D modeling course, and for animation, there is a new course starting next academic year in the master program, which is computer animation. That used to be a seminar, and now it's going to be a regular course. But we were focusing on the rendering, and yeah, at that time rendering was I guess pretty new for most of you, so it was just an abstract term. So I hope now that I succeeded in filling it with content, that you know exactly what I'm talking about when I say, when you hear, or what we're talking about when you hear rendering or projective methods. But I also mentioned shortly ray tracing as another alternative approach for rendering, and like I said, that's what we want to do today. So very quick wrap up projective methods. These are just the slides that I copied from the first time. Projective methods, we have objects like triangles, and the idea is to project them towards a viewer position and then have a 2D projection on our screen of the 3D scene, which is then rendered with the correct perspective and also with the correct lighting conditions. And for example, at that time I asked you what happens if you have two triangles in front of each other, and then you said, okay, then you only have to draw the front triangle. Now I hope you would give the answer, well, then you just look in your set buffer which one is closer. Alright, yeah, and yeah, you know that also you practice that in the practicals, but the year before we always did ray tracing in the practicals, and I also quickly introduced ray tracing as basically the opposite approach. We're using a lot of the same techniques, but the basic idea is just the opposite of projecting everything to the screen towards a viewer. For ray tracing, we look from a viewer towards the screen, and then we define what we see on the screen if we look in that direction. And there comes the name ray tracing from, because we take a ray that is shot from my eye towards one pixel on the screen, and then continues till it hits an object, and then I know this is the first object that I see if I look at that pixel, so I have to draw that object on the screen on that particular pixel. And of course I can then also consider all the things that we also had for projective methods, like light reflection and so on, or I can do some texturing. And in fact, that is one of the big advantages of ray tracing, that I can add recursive ray tracing. I can have then, when an array hits an object, I can say, like for projective methods, we just calculated the normal vector, and then we said, okay, for example, here is a light source, so we then calculated how the light influences this, and then we get a color value for this point here. But for ray tracing methods, we can calculate a reflection vector, and if that, for example, hits an object, and if that object then is reflected to the light, then we also know that this light, of course, influences this point here, and we can do this recursively, and then that's why we get, and of course we could also do this for the projective methods, but it would be a lot of like manual work, and here in ray tracing it fits into the general scheme. We just have to run it over a loop and then recursively get the scene. But as soon as you hear recursive, then it's usually also something where you have to be careful in terms of time, and yeah, that's the point why ray tracing is on the one hand so slow usually, but on the other hand so realistic and natural, because the whole model is set up in a way that it kind of integrates very well into this it considers these natural influences that we have right quite well. Good, yeah, so like I already said, this was done last year in the practicals, and these are two images. I think I already showed them in the first lecture, and that these are not even like the latest state-of-the-art ray tracing. These are still from my predecessor who did the course like 4 years ago. But you see here already that this looks quite realistic, and this would be quite some work to do this with projective methods in such a realistic way. These are some examples from last year, from the practicals, from what the students did in the practicals when they implemented a ray tracer, which were also quite impressive, not as impressive as the previous one, but for practical I think it was quite good. And yeah, hopefully next year I can show some impressive results from you then. So let's look into ray tracing. Yeah, so I already said, if we compare ray tracing with the projective methods, then it just looks like the opposite. And indeed, we usually call or we classify projective methods as so-called object order rendering, whereas for ray tracing we often speak of image order rendering. Actually, it's the other way around. Image order rendering is a type of algorithm, and ray tracing is a special instance of that kind of approach. And the reason why we talk about object and about image is that in one case we run over the objects. So for projective methods, we look for each object, and then we find all pixels that are on the screen that are influenced by that object. So we have a triangle, then we do the projection, and then we do the rasterization. So we know all the pixels from the triangle that appear on the screen. Then we have to do the lighting, and then we have our 2D image. For ray tracing, we do the opposite. We do not only the opposite in terms of the direction that we projected, but we shoot the ray, and then we go, instead of going through all the objects and putting them on the screen, we go through all the pixels and shoot a ray, and then we go to the objects. So if you think about what's the difference here, there are a couple of things, for example, that we don't have to do in ray tracing. We don't have to do, for example, hidden surface removal, so we don't need a set buffer, because per default we always find the first objects when we follow the ray, because that's the first one that we see, and or the only one that we see. Then we don't have to do a perspective projection. We don't need a perspective projection matrix, because it is inherently integrated into this approach, because we are shooting these rays already in a different direction that then gives us the correct perspective. So because the rays are shot in this way, they are already shot in this perspective and consider this perspective, so we don't have to do the perspective projection that we do in the projective methods. But there are also a lot of similar things. You will see today a lot of the basic techniques are similar, and also we can, for example, apply texture mapping. Shading is calculated similarly. In fact, the simple shading model that we had at the beginning was in the book from the chapter about ray tracing. So you see here we apply a lot of the same techniques. The other difference is, of course, in terms of the performance. If you look at it, it actually looks like ray tracing could be faster, and depending on how you do it and what you do, that's actually the case, because in one case you have a loop running over the objects. So if you think about a very complex model with thousands of triangles, you have thousands of objects that you have to take care of, whereas for ray tracing you're running over the number of pixels, which is also a lot, but is a fixed number. So from the asymptotic behavior you would assume that ray tracing is actually better. But of course the critical point is here, find all objects that influence it. So for each pixel you might end up looking to really all objects when you have a recursion, and that is of course then the part that slows it down. Good, so if we look at a very simple way of doing ray tracing, then we can specify it as pseudocode in this way, that we say for each pixel we shoot a ray and find the first object that is hit by the ray, and then we can calculate the normal vector for that point. And then we do the shading, which is basically calculate the pixel color from that value based on the light and the normal vector. Of course, that is very simple, and then you get pretty much the same images as with the projective methods. I mean, basically, it shows that in both cases you could, in theory, achieve the same images. It's just what kind of techniques you have to use to do that. And yeah, so this is a very simple approach where we then just shoot and then just calculate the shading in this one point. So if we want to do this, the first thing we need to do is, of course, we need to calculate a ray, because we want to have a ray that starts at our eye position, or at our viewpoint E, goes through a particular pixel on the screen, and then is shot towards an object. So what would be the most obvious thing to do here? How can we represent such a ray? A vector? Almost. A line, exactly. And what kind of line representation would we use? What's the most natural? We had different representations like implicit, parametric. Yeah, exactly. I would use a parametric line equation, which is defined by a support vector, E, which is a position on the line, and a direction vector. For example, we can choose S minus E, when S is the vector to the point on the screen, to the pixel on the screen. And then we have a line that goes directly from our eye through this point on the screen towards our scene, which is exactly what we want. Now, if we choose these vectors in that way, we can of course also use the vector S as a support vector. But if we choose it this way, we also have a nice characteristic, which is something that that we had on, I think, the first or the second tutorial, where the task was to figure out how this parameter t that you basically use to walk along that line influences it. If we choose E as a support vector, then for t equals 0, we are at the viewpoint. For t equals 1, we are at the position on the screen. And for all t's larger than 1, we are within our scene. So this is basically the area we are interested in when we want to find our objects. And this is why I was asking what kind of line representation you would use, and you were correct. We would use a parametric representation. Now we want to so the viewpoint, of course, is given. We also have to define our viewing window, and then we have to get each pixel on the viewing window. So we have to get our vector S. So we have to we have to somehow calculate it. And yeah, I'm not going to ask it now. The obvious, it's kind of obvious if you think about it. If we have a coordinate system that is at the camera position, then the calculation becomes much easier. So we create a coordinate system at the camera, and I said we're going to repeat a lot of things today, so I hope that this all sounds familiar. We have a camera position E. We have a viewing direction, which is a vector towards the center of the screen that we define. So this is something we have to define. We have to define where we want to have our screen or our projective area placed. And then we can have this view up vector, and I hope you remember the view up vector was a vector that was basically pointing straight up from W and anywhere straight up from W, so you split the space in a left and in a half area. And the only reason why we need that is to calculate rectangular perpendicular vectors for our Cartesian coordinate system. So we can do the scalar product of vector minus W cross vector T, the view up vector, that gives us a vector U that has a right angle to W. Then we can multiply those with a cross product, and then we get a vector V, which has also a right angle to both vectors. And then we have our Cartesian coordinate system by taking another vector pointing in the other direction. Now, any idea why I was choosing minus W and W instead of the other way around? Because it would also work the other way around. It's just a convention. Why did I do that? Yeah, exactly. I didn't see who said it. Yeah, correct. Yeah, you remember we had the rule of right-hand coordinate system, and we made it a convention that we want to have the right-hand coordinate system. It's just a convention, like I said. You could also do it the other way around. It would also work, but you have to make that convention and that decision, and then you have to be aware of it. And I hope now that I mean, that was at the very beginning, and I'm pretty sure a lot of people read that or heard that and thought, okay, yeah, right and left hand, who cares? And but now that you know, for example, the set buffering, where we actually, I think I got myself confused when I explained it, is it minus or is it plus? Then you really have to know, is it a right or left hand coordinate system? So I hope that you learned enough from this course that now when you hear this stuff again, that you can make a little more sense out of it than probably at the beginning. Good. And then, of course, when we want a Cartesian coordinate system, we also have to normalize, and we already answered that question here. Good. So we have our coordinate system now, and then, of course, we have to specify our screen as well, where we want to project it, our projection window. And we can do this in a similar way as we did with the projective methods, where we just say we specify a left side, which in our coordinate system means the value of u equals L. So that's basically a plane here. Then we get a plane for the right side where u equals r. Then we get a top for v equals t. Don't confuse this t with the view up vector, which was a vector t. And we have a bottom for b. And then also we have, of course, to specify the distance d, and that's the distance of the viewing. That's the distance of the origin of our coordinate system, our viewpoint, to the center of the screen, or of the UV plane to the plane that is defined by the screen. And this d is then minus w, because we're looking in the negative w direction. Good, yeah, so that's pretty straightforward, but now we have to, of course, like I said, we want to calculate the position of a pixel on the screen. But this is also something that we already did, not with these concrete values here, but we did windowing transformation when we did, for example, the projection. In that case, I think it was from the for the last step, yeah, for the screen, which is also the case here. So we have a window of n cross y pixels, and we have this specified viewing window that we have, and we want to map them to each other. And we can do this by using these two equations here, which look a little complicated, but you see this is pretty much related to what we already did. So let's just look at the case for the u, which is the left and the right. So we have a left and a right side, and we have for the screen we have a window with the size nx. So it starts with 0 and goes to nx. Let's choose a concrete example to make it easier. We have 100, for example, is nx, and this here is, for example, 1000. Now you see from the image that this 1000 is the left side plus r minus L. That is directly, if you put in the concrete values for left and right, what you need to calculate to get this number of pixels or fields that you have here. Now if we want to match that, for example, if we have a point E here, a point I here, and we want to match that to the relatively same position here, then what we have to do is we just take 1000 divided by 100 times I. So if, for example, I is 30, then we get here 300 pixel, which is for 1000, of course, the right result. So you see here what we have to do is we have to divide the upper length by the lower length, which is exactly what we have here, and multiply it with I. And then you probably also remember that we said when we're talking about pixels, we always deal with the pixel center from, and this is the length of 1. So that means we have to put this plus 1/2 to it. Alright, and for the v, we see the very same. So we can do now, we can calculate now our pixels on the screen, and then we can do our project, or we can shoot. We don't have to do the projection, but we can shoot our arrays. But and like I said, we don't have to do this step from the perspective to do the perspective transformation to then be able to easier do the orthogonal projection. But nevertheless, we might also want to do an orthogonal projection with ray tracing, And if we want to do that, of course we can also do that, but we have to shoot the rays then in a different direction. We don't have to shoot them prospectively, but we're always shooting them in the same direction. So remember, for the orthographic projection, we were projecting always along the z-axis or the negative z-axis, depending on how we specify it. And here, so when we're shooting the rays, we just have to shoot along, in this case, the negative w-axis. So we're just shooting in the same direction, but the other one. So the direction is always minus w, but the origin of these rays, of course, changes now, because for each one we have a different start here, and we can calculate this origin easily for each of the ij's with the formula that we just specified. So the origin becomes, in our new coordinate system, the origin, we go to the origin of the new coordinate system, and then we get the u and the y values with respect to these two base vectors, u and v, and that way we can then, in this direction here, come to, for example, this point here, ij on the screen, or uv on this plane, or vector e plus u vector u plus v vector v in relation to this new coordinate system. Now if we do the perspective projection, then of course we have the same origin for all our rays. By the way, ignore those points here. They are just to illustrate it better, so you see it better that they have no meaning. Same for these black dots here. So they all have the same origin, which is E, our viewpoint, but they have, of course, a different direction. But we can get the direction in the same way as before, because the direction is just a pixel on the screen. So what we do is we calculate the U and the V like before, and that way we come to this position that I also indicated in the previous image here on this plane. But of course we want to shoot it not through this position on this plane. We want to shoot it through this position on this plane if we move it by the distance that we have from the screen. So what we do is we add in minus w direction minus d. So our ray that we have now becomes E, the origin, plus minus dw plus u plus v, whereas in the previous case our array was E plus u E plus u vector u plus v, but it's a linear combination, minus w. So now if you compare those two, they look pretty much the same. The only difference here is this factor d, but the vectors look really different. So what's wrong here? It's wrong. I made a mistake on purpose to make a point. No one? Yeah, I think you mean the right thing. I just wrote the vectors down and added them, but I didn't distinguish between the direction vector and the origin. And that is exactly the point here. Here we have the same origin, but we have a different direction. And the direction is then the vector that we multiply with this factor t to walk along the ray, or to shoot the ray, like I also said. So what we have to do here, so you see I made it on purpose because I left also space here, plus t times this vector, and that is then our array p of t. So the factor here, and then here you also see p of t is t times w. And now of course they still look relatively similar because they go through similar points, but of course you see now that this here is the main difference that just switched. Alright, so we know now how to calculate our array, we know now how to find our point on the screen, we know how to calculate the ray through it. So that is okay. We also know when we hit something how we calculate a normal. What we don't have done yet is how we calculate the hit. So let's look at the intersection. Actually, we know how to do that because this is really just a repetition of previous things. But there are a few things that I add now because we were at that time not able to do that. So, and this is also a good thing, good opportunity to wrap up and repeat and refresh your memory. We had implicit surfaces, and you remember an implicit surface was defined by a function, and if those function values are equal to 0, then the point is on the surface. So that's why it's called implicit, because we cannot explicitly calculate the points, but they are implicitly defined by this equation. So if we want to calculate the intersection of an implicit surface with array, we take the point at array and put it in that function, and if it fulfills that function, that is, if the result is 0, then we have our intersection point, and if not, then we have another point on the array that is not intersecting with this surface. And as an example, at that time, and also that was, I think, an exercise, a question in the first exam, in the midterm exam, we used the sphere. So you remember the implicit. I hope you remember the implicit representation of a sphere. If we put the vector array into that sphere, we can change the order a little bit. I wrote it down here this time, but yeah, that should be really familiar, and if not, then it's really just refreshing your memory, because I hope you understood that, everyone understood this. We see, if we rearrange the values a little bit here, we see that these are the values that we don't know, which is just a parameter t. Everything else is known, so we want to find the t value, and we see this is a quadratic equation, so we can solve this with this formula for quadratic equations. And I hope you all remember, was also an exam question, that you can have 0, 1, or 2 solutions depending on if the ray goes through the sphere, then you get 2 intersection points, of course. If it touches the sphere, then you get only 1 intersection point, or if it doesn't intersect with the sphere, then you get 0 solution, which means that the values under the square root here are 0, and then you get no solution. Now I don't know if you remember, but I remember at that time I was also asking you what happens if you get 2 solutions but one of them is negative, and I remember that I looked in a lot of faces that were like, what the hell is he talking about, or why does he want to know that? But the answer is, of course, if you have a line like this, and this is now 0 in your coordinate system, because you defined the coordinate system there, then of course everything here is negative, everything here is positive. So it means that you are inside of the sphere, that you see the sphere. From this you see only the inside, you see only 1 intersection point from the sphere. And yeah, at that time this was, of course, a lot of people did not understand why you would have something like that. But if you do ray tracing, you see obviously that this can be the case, and that this happens then, that you then get these kind of results, and you know how to interpret them. Good. Then, of course, the other thing we had parametric surfaces, which were not defined by this implicit equation, but by an explicit function. And the characteristic of parametric equations was, or parametric surface was, that we have always 1 parameter less to control it than we have dimensions. So, for example, if we have a line where we usually need an x and a y value to describe it, there is 1 parameter which is just a t value to describe it. We had the other example with the sphere, where 2 angles that are kind of related to the latitude and the longitude, what we have when we describe the map of the world. 2 values, 2 angles are enough to describe the 3 dimensions on the surface of the sphere, or describe all 3-dimensional points on the sphere. And for example, for plane, we also had that we can have 2 we also had that we have 2 parameters to describe it. So, and since we do not plug in a value here to verify it, what we do here is we take 1, which is the ray, and set it equal to the other, and then we solve this equation, and the solutions of these equations are then of course our intersection points. Now what we didn't really discuss that much at that time is that this can be done. We discussed it then later when we talked about the linear equation systems, but that when we talked about the intersection with a plane or a triangle, we didn't talk about it. But of course, you know that these are, you see now that these are three equations with three unknowns, so we can use linear equation system to solve that. And what we do when we, for example, want to when we want to get the intersection with a triangle, or what we often do is when we want to have the intersection with a ray and a object, is that we calculate the intersection with a supporting plane, a supporting surface of that object, and then check if this intersection point is part of the object or not. And for a triangle, this is pretty straightforward. We calculate the intersection of the plane that is defined by a triangle, and then we check if the intersection point is in the triangle or not, and then we have our intersection point, or we know it doesn't intersect. So this is really just a quick wrap up of what we had when we talked about, I hope you remember the term barycentric coordinates. So we can define a plane, or we have a triangle defined by three vertices, A, B, and C, vector A, B, and C. Then we can say we use this to specify a plane in a parametric equation by having one support vector again, which is in this case the vector A, and two direction vectors on the surface of the plane, which we conveniently choose B minus A and C minus A. And that is convenient because then of course we can create this so-called barycentric coordinate system where we have the parameters beta and gamma. So you see we have two parameters controlling a three-dimensional object. And then we have our plane equation. We can put that together with our ray equation, and then we get a linear equation system. So we have here our three equations. Then we can rewrite that, and the rewriting here, if you look at it, you see that we're sorting basically we're putting all the unknown values to one side, and on the right side we have everything that is known. And then we see that we can also write this in this matrix notation. And then you see we have only unknown values here, and these on the left and on the left matrix and the right vector, these are all known values. So we can obviously use what we learned from the Gaussian or the Cramer's rule, that we can how to solve linear equation system. So we could easily solve that. What we could also say, if you write it this way, you see that you can also do it by this way, that you just calculate the inverse, multiply it with the result vector, and then you get your result. So this is basically, we did this, that's basically Gaussian here summarized. So you remember we had this identity matrix then here. Good. All right, so we have our intersection point. Now we need to check if it is, and then we can calculate it by putting the value t. No, we have the parameters t, beta, and gamma, and then we can calculate the intersection point by putting the value t into our line equation. Of course, we could also put the beta and gamma into the plane equation, but that's kind of because they are the same point, so we should get the same result. If not, we have a calculation error. But the beta and gamma are actually more important for something else, which is checking if it is within the triangle. And I hope you remember that we had this, that we argued why these conditions are sufficient to check if it is in a triangle, because the point is just, if you look at the equation that we had, then it's basically, you can represent this p as a linear combination of these two vectors here, and then the beta and the gamma are just the factor that specifies how long those vectors are. So of course they both have to be larger than 0. So this is gamma and this is beta. Both have to be larger than 0, which means it's to this side here somewhere. But of course, if it is too far, then it's not part of the triangle. So we have to check this other condition as well, which means that either beta or gamma can be maximum of 1, and the other then has to be smaller. So this is then basically cutting this part off. So this is then the smaller than beta plus gamma condition. Smaller than 1. And then it is inside of the triangle. Good. Of course, we can also calculate the intersection of array with an implicit plane. We don't have to use the parametric equation, but the parametric equation is often used because we have this easy condition of checking if a point is within the triangle, because the parametric equation leads directly to the representation of the triangles in these barycentric coordinates, which gives us this condition. But of course we can also calculate our intersection point by doing it with the implicit equation. Then we have to put this point, this ray, of course, in the equation, and then solve this equation for the only unknown parameter that we have, which is t. When we have t, we can plug it into the equation, and then we get this value t. And like I said, for triangles, it makes more sense to use the parametric equation. But if we have, for example, general polygons that are also defined by a plane, so the polygon is flat on the plane, then we want to really have this intersection point. For the triangles, we only calculate it if the conditions are fulfilled. But here we calculate the intersection point, and then we have an easy way to check that. You remember what? That was just last time. So, the edges. Yeah, and what's with them? Intersect. Yeah, exactly. You mean the right thing, I think. If you have a point here or here, you shoot a ray in a random direction, and we know now how to shoot rays. And then you calculate the intersection with the polygons. If it is odd, then it is inside. The point is inside of the polygon. If it is even, it is outside the polygon. Pretty simple. Good. So we have our basic ray tracing algorithm now, where we can calculate the rays. We know how to calculate surface normals. I didn't repeat that, so I hope you know that. We know how to calculate the intersection. So the next step is, of course, the shading, the lighting. And this is something I do not want to repeat, because we really did this a lot, and you also had this in the practicals. I hope you did this a lot. So we talked about ambient shading, which is this part here, which is more the global, which is the global, simulates the global illumination. We had the Lambertian shading, which is then creates a diffuse or matte light on the surface, which is this part here. And then we had the Phong shading, which deals with these highlights, these spots, these blinking highlight spots on, for example, a bowling ball. So these are again examples from, so this is one of the spots, and here you also see them. This is one of the examples again from last year's, from the ray tracing practicals. And we had, of course, the Guru interpolation, where we have the vertex, the color, and the vertices, and then we do a linear interpolation with the color. Good. Yeah, and that leads then to our basic ray tracing algorithm, which is basically what we already already said, just a little bit more specified. For each pixel, we compute a viewing ray. Then we check if this ray intersects with an object for all values larger than t larger than 0, because we're looking in a certain direction. And then we compute, if it does, then we compute the normal vector, we do the shading, and then we and set the pixel to that color. If we don't hit an object, then we set the pixel to the background color. And that is a very simple ray tracer. Of course, the results will not be impressive, but you see it's pretty simple and pretty easy and pretty straightforward to implement. And now, of course, we're interested in how to do some more advanced techniques to make some nicer graphics, and that is then the next step after the break.